In this video, we're going to talk about the fundamental theorem of algebra and how it applies to polynomial equations. And as the name sounds, this is very important. This is very fundamental. All right. So what we know is so far is that if we have a polynomial function of degree n, then we can have at most n real zeros. That means it can cross the x-axis n times at most. However, some functions don't have n real zeros, and they don't have n x-intercepts, like y equals x squared plus 2. Well, this has a degree 2, but if we graph it, we're going to get something like this, where our vertex is moved up, and it's going to look something like this, where it doesn't cross the x-axis at all, so it doesn't have any real zeros. All right, so what's going on here? And that's where the fundamental theorem of algebra comes in. Okay, the fundamental theorem of algebra states this: that a polynomial function with degree n greater than 0 has exactly n complex zeros. So it's exactly n complex zeros. Now remember that a complex number is in the form a plus bi. That's a complex number where this I here is our imaginary unit. Okay, so this I is our imaginary unit, which is the square root of negative 1. Okay, so these are complex numbers. All right, so let's see how this works out. So let's look at a specific example, another parabola here, similar kind of situation. So we want to find all the zeros of this 2x squared plus 8. All right, so again, let's sketch a quick graph here. And somewhere up here at 8 is going to be our vertex, and it opens up, the parabola does. And it's going to be a little steeper. It's going to look something like this. So there's our graph of f of x. Okay. So we have our graph, and it doesn't cross the x-axis at all, so we have no real zeros. Well, by definition of a zero, what has to be true here is 0 equals 2x squared plus 8. And let's go ahead and solve this. If we subtract 8 from both sides, we get negative 8 equals 2x squared, divide by 2, and we have negative 4 equals x squared. Next, we're going to square root both sides. And because of our negative here, we've got the square root of negative 4. Well, we're going to have to break that up. I'll write it out, even though we don't always write this out, as square root of 4 times square root of negative 1 equals x squared. We're also going to need a plus or minus out here when we take that square root. And so the square root of 4 is going to give us 2. And the square root of negative 1 is I. Normally we'll just jump right to here, but there we go. No, my squared came hanging out here. And so we have our x. All right, so we've got two zeros. Our zeros are our x equals positive 2i and negative 2i. So they're imaginary zeros here, okay, or they're complex zeros. So we always have, again, exactly n complex zeros. This degree here, n equals 2. And so we expect two zeros. There they are, and they're both imaginary, which means they're not actually x-intercepts on the real axis. Okay. So now let's take that fundamental theorem of algebra and we can combine it with another important theorem called the linear factorization theorem. So if we've got a polynomial that's of degree n greater than 0, well, we know that it can be factored in this form. Right here we have some a value times x minus z1, x minus z2, so on and so forth, where these are all the zeros, z1, z2, and z blah, blah, blah. They're all the zeros, okay? This, oh, and notice this. Notice this is 1x, 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 okay? And the reason is because we factor out this a value. And if we factor out this a value, then we can always write any function in this form. Okay, so for example, we just found out for this polynomial, this is the same one from our last example, we just found out that the zeros are, we had 2i and negative 2i. Okay, so those are our zeros there. And so according to our theorem here, we should be able to factor f of x as our a value, which is 2. That's the a value from right here. Okay. Then we're going to have x minus 2i and times x plus 2i. Okay. So that would be x minus our first 0, positive 2i, that went right here. And then x minus negative 2i gives us this. All right, and so that's our linear factorization. Now, let's double check this. There's really our answer. Let's check this by multiplying this out. Okay, and so let's leave the 2 out here for now. We're going to multiply our x and our 2i, so we have x times x, which is x squared. We have x times 2i, which would be plus 2i. We have negative 2i times x, which is minus 2i. Oh, I lost an x here. Minus 2ix. And then we have negative 2i times positive 2i. And that's going to be minus 2 times 2 is 4, and I times I is I squared. Okay. Now, keep the 2 out here for a moment. Let's clean this up. We have x squared, and here these cross out. They make 0. And we have minus 4, and we have times I squared. But I squared, since remember I is defined by the square root of negative 1. So if we square these, both sides here, we get I squared is negative 1. Okay? So this is really, come back down here, negative 1. So our I squared is just negative 1. Okay? And so now we can clean this all up. This is just 2 times x squared plus 4, and that gives us 2x squared plus 8. And so we verified that, yes, this linear factorization theorem up here does work. Okay, again, we took the a value, put out in front, and we used our zeros to write the factors. All right, so important thing to note here, complex zeros are always come in conjugate pairs. Okay, so if a plus bi is a 0 of polynomial, then a minus bi is also a 0. So in other words, if we have 3 minus 5i, if that is a 0 of a function, then 3 plus 5i would also be a 0. That has to be. All right. So let's try another quick example here, simplifying for standard form. So try this. Go ahead and you can pause the video and take this problem here. We want to write the polynomial in standard form and identify the zeros of the function and the x-intercepts of the graph. Okay, verify your answer on your graphing calculator. All right, so try that. Go ahead and pause that, see what you can come up with here, and then after you got some answers, hit play, and I'll show you what we can come up with. So here we go. Let's work it out. First of all, we notice that right here we got x plus 1. That tells us that our real zeros, or our x-intercepts, is going to be 1, it's going to be negative 1 actually. So our x equals -1 is the only place that this graph will cross the x-axis. All right, we have other zeros, so all of our zeros, let's list them all. All of our zeros are -1, and then we have the number that makes this 0 would be -square root of 2i, so -square root of 2i, and positive square root of 2i. Sometimes we write that as plus minus square root of 2i. Again, fundamental theorem of algebra states that we should have 3 zeros, and as we multiply this out, we'll see we have a third degree. Okay, so let's go ahead and do that multiplying and write it in standard form. Let's start with multiplying these right 2. Okay, so we're going to get x times x is x squared, and then we're going to distribute this out. So we got x squared minus the square root of 2ix, and then we're going to distribute the square root of 2I here, and we get plus the square root of 2ix, and then we get minus square root of 2 times the square root of 2 is just 2, and then I times I, we'll write it as I squared for now. Okay, so this will be 2I squared. Cleaning that up, we have x plus 1 times x squared, and these guys cancel out. And remember that this is, I squared is -1, so we have -2 times -1, which will give us positive 2. All right, and then multiplying this out, we get x times x squared is x cubed plus 2x. Distribute the 1, and we get 1x squared plus 2. So in standard form, we have f of x equals x cubed plus x squared plus 2x plus 2. All right, so there's our standard form. Okay, and we see that it's third degree, so we have 3 zeros. And the only real 0 is x equals -1. And so that is our x-intercept. All right? And if we graph this on our calculator, we'll see that it crosses at -1 down here. And we should have, well, let's take a look at it here. So here's a little picture of it down here. You'll notice that we have exactly one real 0 here at -1, and that's the only time it's going to cross the x-axis. And one last quick example here after we note some key connections here. So we've seen that all of these things are really saying the same thing. If we say x minus k is a factor of f of x, well, that means that k is a 0 of the function. Or that's really just saying that f of k equals 0. Okay, so x equals k is the root or the x-intercept. All right. So those are all the same. So one last little example. Let's find all the 0, even the complex ones. So here we have a function that's a quartic or a 4th degree, and we want to start using our graphing calculator. Okay, and so let's look at a graph here. So graphing on our graphing calculator, we get a graph that looks like this here. We notice we have 2 real zeros at x equals -1 and x equals 2. So that gives us a clue here that we can factor this, and let's use some synthetic division here. So we got our coefficients 2, -4, -1, 3, and -2. And using the fact that we have these 2 real zeros, let's break it down. So we have -1. Going to bring down the 2. And we multiply -2. We add -6. Multiply -1 times -6 is 6. Add, and that gives us -7. Oh, I forgot a term. Oh, that's not a -13. Got to write this carefully. Let's try this again. Okay, Let's spread this out. We've got 3 and negative 2. Okay, and again, we multiply, we get 6. We add, and we get, what is that, 5. Multiply, negative 5, add, negative 2. Negative 1 times negative 2 is 2, and we add and we get 0. That's what we expected because we knew that negative 1 was a 0. Okay, now we're going to take this leftovers down here, and which represents a cubic, and let's rewrite those because I'm out of room. Negative 6, 5, negative 2, and let's factor those using our other 0 of 2, which we get from right here. This is our other real 0. So we factor this down, bring down the 2, multiply, we get 4, add negative 2, multiply, 2 times negative 2 gives us negative 4, add 1, multiply, 2, add 0, and there we have it. And so we've just factored this, and we have, we can say this, g of x equals, okay, now we've got our a value here is 2, so we're going to start by, well, actually, let's leave that alone for now. We have more than a linear factor. So we have x plus 1, that's for our negative 1, 0, times x minus 2 times, I'm going to run out of room here. All right, moving over a little bit there, and we see that this is our remainder, or it's what our last factor after we divide out those first two factors. And so we have 2x squared minus 2x plus 1. And again, that comes from these guys right here. Okay, now if we check, we'll see that we cannot factor this. So we found 2 zeros so far, and let's come down here a bit. Now we need to find out when is 2x squared minus 2x plus 1 equal to 0. And we're going to need to use our quadratic formula for that. So we have x equals negative b, which is positive 2, plus or minus the square root of b squared, which is negative 2 squared, minus 4 times a times c, which is 1 all over 2 times a. Okay. And this is going to clean up to 2 plus or minus, and we have 4 minus 8, which is negative 4. So the square root of negative 4 all over 4, which is going to give us 2 plus or minus 2i all over 4. And with a little canceling here, remember that we've got to cancel both ways. So 2 goes into 2 once, 2 goes into 2 once, 2 goes into 4 twice. Okay, so we end up with 1 plus or minus I over 2. Okay, and so our zeros are, we have negative 1, positive 2, those are our real zeros, and then 1 plus I over 2, and 1 minus I over 2. Okay, and there's our zeros. Okay, now we went a little too far there. Okay, so let's back up here, read the directions carefully. Our real zeros, we found out, are x equals negative 1 and positive 2. Those are the real zeros. The question now is, do we have any complex zeros with imaginary parts? And yes, we do. And why is that? Because the fundamental theorem of algebra says we're going to have exactly four zeros. And we just found out that 2 of them were real, and we jumped the gun a bit, but that means that we must have exactly 2 imaginary zeros. Okay? All right, so that's how the fundamental theorem of algebra works, and In the next video there we have some more examples for using that. Again, we can use our graph to give us the real zeros, but that's only half the story in this case. Good luck.